All right, we've had a dramatic pause there. So I was talking about simplifying this formula further by eliminating mass. But which mass is this? Is this mass 1 or mass 2? This mass right here is always the one that is spinning around the other mass. So say the moon is spinning around the earth, then we would cancel this and the moon, and the earth would remain. So just say this is the spinning mass, the one that is going around the other. That's the one that cancels. So that's the one that's in the center. So we have RG M2 equals V squared. All right, that is a simplified version of the original, and I recommend jumping to it in order to do these problems. So let me give you a problem to look at. Let's say that we have a 11 kilogram mass. So if you would sketch that, and a 15 kilogram mass. And they are 1.2 meters away from each other. So I'm going to leave the simplified version here and erase everything else. And recall the mass here is the mass that is spinning, or the mass in the center, it's not the spinning one. Now, in this case, I have 11 kilogram mass and a 15 kilogram mass, 1.2 meters from each other. Notice they are just sitting there on the table. They are not rotating around one another. Still, there is a gravitational attraction between these two masses, and the formula can give it to us. G, force of gravity, equals, let me lowercase this g, big G M1 M2 over r squared. And we can just take the numbers that are presented here and throw it into the formula and see what comes out. In this case, where we don't have one thing spinning around the other, we will not use the simplified version. We'll just head on into this one. So G is 6.67 times 10 to the minus 11. Mass 1 is 11. Mass 15. Mass 2 is 15, and it's divided by 1.2 squared. If this isn't spinning around this one, you'll notice r is just the distance between the two. So r takes on that in this scenario. When I plug that in the calculator, I come out with the force of gravity. If you would plug it in to give you good practice with that EE button there. 7.6 times 10 to the minus 9, and it's a force, so you won't be surprised that the unit for it is newtons. Now that means 0.000000076 newtons. That's what that number means. From that, can you tell me if you suspect that force of gravity is a strong force or a weak force? It is very weak. Gravity is an extremely weak force, and that's why we don't have a lot of experience observing it in our world, because we don't have a lot of mass to look at. For example, if I had a salt and pepper shaker, these are not salt and pepper shakers, but imagine they are. Suppose I set them here on my stove, and this has a mass, that has a mass. Any two objects with mass on the whole planet, in the whole universe, will experience the force of gravity on one another. So there is a force of gravity from this mass to this mass. And we could plug it, if we knew the mass of these salt and pepper shaker actors, we could put it into the formula and come up, if we knew the distance between the two, we would know the force of gravity between them. And that works both ways. It'll be the force of gravity from this attracting this and this attracting this. So if we came up with a number, it would be on both. So the force of gravity works two ways. It'll attract the red to the green, and it'll pull the green to the red. So if there is a force of gravity between these two, why are they not being pulled together? The force of gravity is attractive, so why isn't it pulling it? If this is pulling on that and that's pulling on that, why are they not coming together? And the answer is the force of friction again. Because gravity is such a weak force, these objects will not move toward each other because the force of friction between them and the surface they are on is greater than the force of gravity. So, all right, I'll put our little salt and pepper shaker actors away and pull out our next example. I think this will be it for today, and I said it wouldn't be a real long lesson. And let's look at one more example. This time we will take a massive object, the Earth, and the Earth has a mass of 5.9 times 10 to the 24 kilograms. And let's take, we also need to know the radius of the Earth. I'll put it up here. So Earth radius is 6.3 times 10 to the 6th meters. So that's Earth radius. And we'll grab that in a minute. And we'll say there's a 1.0 kilogram object 1.2 meters above the Earth. So 1.2 meters above the Earth. This is not drawn to scale. And here's a 1.0 kilogram object. So there it is. So I want to know the force of gravity, the force of gravitational attraction between the Earth and the object. So there'll be a little bit slight differences on this, the way we calculate this, than what you just saw with the 11 and the 15 kilogram masses that were just sitting on the table. And here's why. The force of gravity equals G m1 m2 divided by r squared. So we begin our calculations by throwing in 6.67 times 10 to the minus 11. That takes care of our G. Mass 1 is now the Earth, so we grab this big number, 5.9 times 10 to the 24. And again, I put that in 5.9 EE 24, and it saves me a few keystrokes. Mass 2 is 1, and that is divided by r squared, r being 1.2 squared. Now that is wrong, actually. And that is why it's different when we're using massive objects than we're using 11 and 15 kilogram objects. This number r is the distance between the two, but it's the distance from the center of one object to the center of the other. Now when we were using the 11 and the 15 kilogram objects, they were so small, we didn't care about the center to the center. But when we're using an object as big as the Earth, we are going to have to change this and include the radius of the Earth. So we're going to have to go from the center of the Earth to the surface of the Earth, which is just the radius of the Earth, Earth's radius, and then add the 1.2, which is how far the object is in addition away from the surface. So I'm going to add 6.3 times 10 to the 6th. Let me stretch that out so you can see it well. Squared. So when I calculate all of that, I find that the attraction between the two, the force of gravity, is 9.8 newtons. There's an old friend. You might wonder why we say that the acceleration due to gravity is 9.8 meters per second squared. It's also embedded in this idea of the force of gravity between the Earth and objects near the surface of the Earth. So, force is 9.8 newtons. So that's an old friend of ours. Alright, I'm going to end this video here, and actually I didn't get to the point where I used that abbreviated form of the force of gravity, but I have you set up to use it when we get together again next time. So take notes on this, and that will be proof enough that you saw this video, and enjoy the rest of your time off. Be ready to just forge ahead when we get back together next week. Over and out.